So our next speaker is Pankaj Kapari from IISER Bhopal, and he will be speaking on primitivity of pseudo-periodic mapping classes. Over to you, Pankaj. Please begin.
So my slides are visible, right?
Yes,
Screen.
perfect.
And I'm also audible perfectly.
Yes.
Okay. Okay. Thanks for the organizers for inviting me to this conference to give a talk. And so I'll talk about primitivity of pseudo-periodic mapping classes and actually in general for reducible mapping classes of infinite orders. So this is a joint work with Professor Ravi Sarthi. Okay, so let's start a talk. So I'll start with some notations. And so this SG will denote a closed orientable surface of genus at least 2. And mod SG is the mapping class group of the surface SG, which is the group of isotopic classes of orientation preserving homeomorphisms of the surface. And this TC will denote a left-handed Dane twist about a simple closed curve C. And this ISG will denote the Torelli group of SG. And this mod SG bracket M, this will be the level M congruence subgroup of mod SG. So I'll define these two subgroups later on. Okay. Now I'll just move on to the problem. So for given mapping class F, we say that some non-trivial element G is a root of F of degree n if there exists some integer n which is greater than 1 such that the nth power of G is equal to F and the order of G is n times the order of F. So basically we are finding roots of mapping classes, and I'm also putting this condition that order of G is nth multiple of order of F for in the periodic case. Infinite order case, the condition is redundant. And so if a mapping class does not have any root of degree n for any integer n, then I say that the mapping class is primitive. Now the question is, given a mapping class, can we decide if the mapping class is primitive? And if it is not primitive, so can we determine what are the roots of this mapping class, at least at the level of conjugacy? So can we determine at least the level conjugacy classes of roots of mapping classes? And so we call this problem the general primitivity problem in the mod SG. Yeah, so before moving on to the some results, I'll just give this famous Nielsen-Thurston classification of mapping classes. So a collection of disjoint non-isotopic essential simple closed curve is called a multi-curve. And and we say that a mapping class is periodic if it has finite order, and it's reducible if the mapping class preserves some collection of curves, or basically it preserves a multi-curve on the surface. And such a multi-curve is called a reduction system for the mapping class. And a mapping class is pseudo-isop if it preserves isotopic classes of a pair of transverse measured singular foliation on the surface with stress factor lambda, which is bigger than 1. So when this mapping class preserves two foliations, so it stretch one foliation by a factor of lambda and contract another foliation by the same stress factor lambda, but and this lambda is bigger than 1. Okay, the classification says that every mapping class must be either periodic, reducible, or pseudo-isop. And furthermore, the pseudo-isop mapping classes, they cannot be reducible and they cannot be periodic. So pseudo-isop mapping classes are infinite order irreducible maps. But there can be intersection between the two collections of mapping classes which are periodic and reducible. So a periodic mapping class can be reducible as well. Okay, so now I'll just start with some developments in the direction of the primitivity problem. So the Fehrenbach and Loss, first they computed some algorithms for determining roots of pseudo-isop mapping classes on punctured surfaces.
Algorithms.
What are there any questions? Okay, so and later on, using the flipper algorithm due to Marx-Bell, one can determine primitivity of pseudo-isop mapping classes even on closed surfaces, and one can compute the conjugacy classes of their roots also. And this algorithm is implemented in Python. And later on, the conjugacy classes of roots of periodic mapping classes has also been classified. So kind of we have already done with the cases of periodic and pseudo-isop. So we are left with the case of infinite order reducible mapping classes. And in that direction, the Margaret and Slammer, they were first they were first to construct roots of dentist about non-separating curves. So for roots of separating curves, it is easier to construct roots. But for non-separating curves, they were the first to give some examples of roots. And later on, the conjugacy classes of roots of products of commuting dentist has been classified by several authors. We now in this talk, we present a solution for this problem for the reducible mapping classes of infinite order. Okay, so before that, I'll give some examples. So we know that any periodic mapping class in the mapping class group must be of order at most 4G plus 2. The 4G plus 2 is the highest order. So if you have any mapping class with order at more than 2G plus 1, then it has to be primitive. And if you take a polygon, 4G plus 2 sided polygon, and you identify opposite sides, you get a genus G surface. And then you take the 2 pi over 4G plus 2 rotation. Okay, so that is a square root of 2 pi over 2G plus 1 rotation, right? You just take the square, you get the 2G plus 1 rotation. So the 1 click rotation is a square root of 2 click rotation, basically. The simple, easy examples. And the one example of root of a separating dentist. So what you do, you take a separating curve. Like in this example, I have a genus 2 surface. The separating curve is C. So you fix one side of the one subsurface of one side of C, and then you twist other side by pi. And in that way, you get a half twist of which is a square root of a dentist about this curve C. So such examples are easier to construct. And for non-separating curves, you can see in the left-hand side figure, I have drawn some curves. And if you use the chain relation in the mapping class group, then one can show that this mapping class TA square TB TC inverse times TE. If you take its third power, then you get the dentist about E. And this E is a non-separating curve. So you get a third root of a non-separating dentist. And these examples were actually described by Margaret Slammer in 2009. And if you see the right-hand side figure, it's a genus 4 surface, and where I have a free rotation by 2 pi by 3. And if you compose that periodic map, the 2 pi over 3 rotation, by one of the dentist TC or TC1, and if you take its third power, then you get all the dentist TC1, TC2, TC3. So basically, this mapping class F is a third root of a multi-twist, or this commuting product of commuting dentist. And in the mostly the idea is basically if you want to construct these roots, you take periodic mapping classes or you take periodic maps, and then you take some orbits of those periodic maps of same size and remove some disk around those orbits and attach annuli by twisting them. So you twist some annuli and then attach. Like for example, in the right hand side figure, you just take a order 3 free rotation of the torus, and you take 2 orbits of size 3. You remove some small disk which are like pairwise disjoint from the each point in the orbit of this, and then you attach annulus between them for each orbit from 1 to 1 correspondence. You attach one annulus, and then while attaching, you just twist it by 2 pi, so that you get 3 curves. Overall, the genus will be 4. You will get 3 curves, and where this map will be acting by twisting all those 3 curves. So basically, you get a third root of this product of dent twist. So that is basically the idea, to construct roots of multi-twist or dent twist. Okay, so now I'll just move to the reducible mapping classes of infinite orders, and for that I need a some canonical reduction system, because the reduction system may not be unique. So a reducible mapping class can have many reduction systems. So if you want to work with these reducible mapping classes, we need one reduction system which is canonical, and that one can obtain by taking the intersections of all maximal reduction systems. So this intersection is canonical. For example, if you have a periodic mapping class, even though this mapping class is reducible, its canonical reduction system is empty. So there are no curves in the intersection of all maximal reduction systems. For a dent twist, the canonical reduction system contains only that curve about which you are twisting. This dent twist actually preserves all the curve in the complement which are disjoint from C, but in the canonical one, you get only one curve. Similarly, if you have a multi-twist, which is the products of powers of dent twist about disjoint curves, the canonical reduction system will contain all these curves about which you are twisting. Okay, so how we can use this canonical reduction system to understand reducible mapping classes of infinite orders. So basically, you cut the surface along these curves of the canonical reduction system. So, and when you cut along these canonical reduction canonical curves, in the complement of the curves, you will get some like while cutting, you get maybe disconnected surface, and in the complement, this reducible map might permuting those components. Okay, so what you do, you take high enough power so that all the permutations get killed and all the periodic components also get killed, right? Because in the complement there can be two kinds of mapping classes due to Nielsen-Thurston classification, either periodic or pseudo-ensemble. So you just kill all the periodic maps by taking a high enough power, and now your f2 power n is equal to some products of Dehn twist about those curves in the canonical reduction system, and some other pieces which can be either pseudo-ensemble or identity, because we have already killed the periodic part. This is the canonical form of a reducible mapping class, and this integer n, we call it a degree of the reducible mapping class, and this n is, we take a least integer, and we say that a reducible mapping class is pseudo-periodic if there are no pseudo-ensemble components in its canonical form. So basically, pseudo-periodic mapping classes are precisely roots of multitwist, because if you see in the canonical form, these f1 to fs, these are either pseudo-ensemble or identity. If there are no pseudo-ensemble, that means you just have identity components. So basically, you have nth degree roots of multitwist, which is this tc power q1 times all these product tcl power ql. Okay, so that is the last observation, that any pseudo-periodic mapping class has to be a root of some multitwist with the same degree as the degree of the reducible mapping class. So we had two notions of degree now. One is the degree of the roots, and one is this degree of a reducible mapping class, and they actually coincide for the pseudo-periodic mapping classes. And if this pseudo-periodic mapping class f is a root of, say, that this multitwist, then I'll define this qf to be the minimum of all the powers after taking the modulus sign. Okay, so this particular qf I'll use later on. Okay, now I'll give some examples of canonical forms of some reducible mapping classes. Suppose I have this genus 2 surface and there are 5 curves, and I also have a order 2 rotation of this genus 2 surface. And let's take a mapping class capital F to be TA TB times sigma. So sigma is the order 2 map. And if you apply the chain relation, then you will get that f to the power 12 is TC square. Okay, so that means f is a 12th degree root of the Dehn twist TC square. Here this Dehn twist is actually separating a curve. So you have the canonical form of this f to be f to the power 12 TC square. So this is a pseudo-periodic mapping class of degree 12, and the QF is 2 here, obviously. And I'll take one more example. This is TA TB inverse sigma. In this case, so you note that I'm taking power 2 because in the complement of this separating curve, this separating curve is the canonical curve, and the complement, this because of sigma order 2 map, the two components, they get permuted. So I have to take a square to fix them. So here also, if you take g square, now two component will get fixed, and you will get TA TB inverse, TA TD inverse. Okay, so this is the mapping class. And now if you know pseudo-ensemble mapping classes, then you can observe that in the complement of the curve, this TA TB inverse, this is pseudo-ensemble, and also TA TD inverse is also a pseudo-ensemble. So G is not a pseudo-periodic mapping class. It has two pseudo-ensemble component. Okay, so now I'll move to the normal form for a reducible mapping class. And now we have already seen that sometimes we have to take powers of f in the canonical form, and actually we want to avoid those powers. So if you want to avoid those powers, you have to consider the orbits of curves and orbits of those connected components of the complement of the curves. And these orbits are formed by the action of the mapping class f. Okay, so and if you are considering the orbit, that means you have to consider the mapping classes of disconnected surfaces. So to define some particular mapping classes of disconnected surface, I'll introduce this notation SP. This is disjoint copies of P disjoint P copies of surface S, and this sigma P is a P cycle which permutes these P copies. So if I have a mapping class F in mod S, then this composition F sigma P is a mapping class in the mapping class group of the disconnected surface SP, and this all these P many copies form a single orbit under this mapping class f sigma p. For example, here, if I have TATB sigma 2 and TATB inverse sigma 2, they both are mapping class supported on disconnected surfaces which are formed in two orbit, or which forms an orbit of size 2 of torus. There are two tori, and these two mapping class supported on this union of disjoint copies of two tori. Okay, so now if you don't take powers while cutting the surface along the canonical curves, and if you consider all those periodic all those orbits of curves and orbits of connected components, you can write f as products of some g times gi sigma pi. So these gi sigma pi are pseudo of components, and the g is the pseudo periodic part, because there are some periodic parts. You collect all of them, they are supported on some disconnected surfaces, you call that pseudo periodic, and other part you just remain with the products of pseudo-isops. So this is in a normal form. One example is here, that which I have already taken, TATB sigma. This is already in its normal form with pseudo-periodic component TATB sigma, and this TATB inverse sigma is also already in normal form, and it has pseudo-anisop component TATB inverse sigma. Okay, so now I'll move to the primitivity of reducible mapping classes. So if I have a reducible mapping class, I'll write it in its normal form, and then the f is primitive if and only if at least one of g or this product is primitive, and if both are not primitive or f is not primitive, then a root, you can construct a root of f by individual roots of these pieces, pseudo-periodic pieces g and the product of sigma I, gi sigma I, and the degree of that root will be the least common multiple of individual degrees. Okay, so how do we construct roots of these pseudo-periodic maps or these products of pseudo maps which are supported on some disconnected surface which are in the same orbit? So observe that if I take this f sigma p, and this is a orbit of size p, mapping class supported on a orbit of size p, and if you take the pth power, then you'll get these products of p many conjugates, and each of them is supported on a orbit of, each of them is supported on a connected surface. Okay, so that means this f sigma is actually a degree p root of this product. And what happened in general, that this f sigma p, if you take uth power, then it decomposes into GCD of p comma u copies of this particular maps. So basically what is happening, that you can construct roots of such maps supported on disconnected surface by combining the orbits, right? Since while taking power the orbits get decomposed, so if you want to construct roots, you can combine the orbits and while simultaneously taking individual roots, right? This f is a root of f to the power u over GCD of p comma u. So in general, what will happen, that if I take two such mapping classes f and g, which are which are supported on disconnected surfaces, and there are several orbits of size sigma pi, and for f sigma pi p prime I prime, and then g to the power m is f, if and only if, what will happen, that for each I you need some I prime such that ui divides m, where m is the LCM of all ui's, and then there are some condition on these orbits, that how do you combine the orbits to construct the roots, or when you take powers how orbits get decomposed, that comes from the second observation, these second and third condition, and the last condition comes from the how many orbits were there previously before taking power, or basically since before taking power you have sigma pi many orbits, and after when you get f you have sigma pi prime orbits, right? So they must be same. So these are just, we are reconciling how many orbits are there, and you can see the last condition, this says that one orbit decompose into GCD of pi comma ui many orbits, so s prime has to be equal to sum of these GCDs. Okay, so now you apply these results to find the roots of mapping classes of infinite orders, reducible mapping class of infinite order. So in general, if a mapping class is given you as a product of a Dehn twist, because mapping class could be generated by a Dehn twist, you can determine the type of this mapping class using the curval algorithm, again by Mark-C Bell, already implemented in Python. So if it is periodic, then one can use the result already known by Dhanwani Sarthi. If it is pseudo-sub, one can use the Philipper algorithm. And if it is infinite order reducible, then you just compute the canonical curves from using the curval algorithm. You write the f in the normal form, and you use all these results, like you use theorem 1, and step 2 and 3 for finding individual like roots of individual pieces. They can be periodic as well as pseudo. That is the basically idea for in solving the determining the primitivity of arbitrary mapping classes. Okay, so I'll give one example. I'm running out of time, I think. Okay, so take so this is very made up example. You take this mapping class F, which is TATV cube, TATD power 4 TC inverse. Again, if you chain relation, you will see that this is a sixth root of den twist TC, which is separating curves, and it had two periodic components. TATV cube is also periodic in the torus. TATD power 4 is also periodic in the torus. Okay, and they both are not primitive. They have square roots. So we combine those square roots to form a square root of the original mapping class. Okay. Okay, so later on in this result, we obtain what can be the highest degree of a root of pseudo-periodic mapping class, highest degree root. So it was already known that for non-separating den twist, highest degree is 2g minus 1. So a root highest root can have degree at most 2g minus 1, and they are also realizable by infinitely many genuses. But in general, if your canonical reduction system is non-separating, so the now I'm not talking about one curve is non-separating, I'm talking about the whole canonical reduction system. The collection of disjoint curves is non-separating, means if you cut the surface along those disjoint curves, then surface still remain connected. So if that is the case, then highest degree can be 2g minus 1 times that particular QF that we have defined before. And if the canonical reduction system is separating, then the highest degree is this QF times 3 times g plus 1 g plus 2, and these bounds are realized by, or they are always realized by roots of powers of den twist for infinitely many values of g. And as a corollary, we get that for a separating den twist, the highest degree can be 3 times g plus 1 g plus 2, and this is always realized. Okay, so now I'll define these level M and Torelli groups. So you know that the mapping class group, all homeomorphism, they act on the homology. So, and since this action is invariant under homotopy or isotopy, you get a action of the mapping class group at the level of homology. And since it's a invertible, mapping classes are invertible, you get these mapping classes, you get the image in the symplectic group. Okay, so so there is a symplectic representation, and the kernel is called a Torelli group. And if you further compose this symplectic representation with the modulo M map from the symplectic group to the symplectic group with coefficient in the ring Zm, then you get in the kernel, you call it the congruence subgroup of level M. And we also determine bounds for these Torelli group and congruence subgroups. So if you take a pseudo-periodic mapping class from the congruence subgroup, and it has some roots of degree n, and now I'm assuming that this canonical reduction system does not contain any separating curves, because the highest degree is already realized by separating roots of separating curves. So in that case, if this mapping class lies in the Torelli group, then the highest degree is g times g minus 2 times this QF. And if it lies in the level M but not in the Torelli, then the highest degree increases. It is 3 times QF times g minus 2. And also they are always realized by powers of such mapping classes like TC1, TC2 power k, where C1 and C2 are homologous non-separating curves. And in particular, if you have a bounding pair map, that is TATB inverse, where A and B are non-separating and homologous, then the highest degree is g times g minus 2. Okay, so now I'll finish this talk with the normal closure of pseudo-periodic mapping classes. Okay, so if we say that the mapping class group is normally generated by some mapping class, if the whole conjugacy class generates the mapping class group. Okay, now we know that the mapping class group is generated by non-separating den twist. All of them are conjugate, and therefore the mapping class group is normally generated by den twist about a separating curve. And later on, Lanier and Margaret, they gave some similar result for periodic mapping classes, that every periodic mapping class of certain type always normally generate the mapping class group. And we generalize that result for pseudo-periodic mapping classes, and it says that if genus is at least 3, and you have a pseudo-periodic mapping class with at least one non-trivial periodic component, and that is not a haploptic involution, okay, then the mapping class group is normally generated by such an mapping class. And as a application, we obtain another result. So before that, there is one observation, that this the mapping classes which are powers of den twist, and I'm taking non-trivial powers, and bounding pair maps, they cannot generate the mapping class group normally. Why? Because this TATB inverse already lies in the Torelli group, which is normal, and the TC power k lies in the level k subgroup of the mapping class group, which is also normal. So they cannot normally generate the whole mapping class group, but we prove that they have roots. There are roots of these maps which normally generate the mapping class group. So we constructed those roots using periodic maps, and those periodic maps are not hyperptic involution. So our previous proposition gave us this result, that there are roots of bounding pair maps and powers of den twist which normally generate the mapping class group. Okay, I'll end my talk here. Thank you for listening.
Thank you, Pankaj, for the nice talk. Any questions? If not, let us thank the speaker.
Okay.
Thank you very much.